It's an incremental algorithm. You are going to add like side by side. Okay, you are going to add one side at a time. Okay, but it's also randomized. It's also randomized. So what happens is that, okay, first we compute the convex hull of P. Okay, as I said. Okay, only convex hull, only the vertices in the convex hull of P will have cell anyway, right? As we have proved earlier. Okay, so we are going to take the vertices of the convex hull, and then we are going to sort them. Well, not exactly sort them, just put them in random order. Okay, we randomly, give them order. Okay, so let's call this random order to be P1, P2, P3 up to PH. Okay, so these are the vertices in the convex hull of P. Okay, so now it's a tricky part. Okay, in the first round, we are not creating the farthest point vulnerable diagram. Not yet. Okay, so we will remove the points one by one from P4 to from pH to pH minus 1 to pH minus 2. So we remove the point in a reverse order. Okay, in a reverse order. So every time we remove a point, okay, of course, before you remove pH, you remember, which two sides are your clockwise and the counterclockwise neighbors. In the vulnerable diagram, remember, like sides have order, right? Has certain order, right? Okay, even though now you randomly insert them. Okay, you randomly insert them. Okay, but still okay, at this point, say you have, let's assume you have 10 sides. Okay, you have 10 sides. Okay, you can still consider its clockwise and the counterclockwise neighbors, right? Right? Okay, so of course, like I don't have a figure. Okay, so say, oops. Say you have okay. Let's say we have 1, 2, 3, 4, 5. Okay, so we call this one P1, P2, P3, P4, and the P5. Okay. So let's start removing the side. Okay, from P5, okay, P4, P3, well, actually up to P4 only, okay. So when we remove P5, we remember, okay, the clockwise neighbor for P5 is P3. The counterclockwise neighbor for P5 is P2. Okay? Okay? So we remember these two. Okay, then we remove it, right? And then we can consider removing P4. Before removing P4, we remember the clockwise neighbor for P4 is P2. The counterclockwise neighbor for P4 is P1. Okay, before removing P4. Okay? So we do this. So understand? You guys understand, right? Okay, this should be easy, right? So this is what we are doing. Okay, but keep in mind, okay, this is originally I said this is P4, this is P5. Okay, let me try to create a little bit complicated case. Okay, because the case I created is not complicated enough. Maybe P4 and the P2, right? So in this case, when we removing P5, the clockwise neighbor is what? Is clockwise is P3. Counterclockwise is P4, right? Right? And then, after removing P5, the clockwise neighbor for P4 is P3, not P5, okay? The P5 is gone, okay? So the clockwise neighbor is P3. The counterclockwise neighbor is P2, right? Okay? Just want you guys to understand, okay, what we are doing here, okay? So the left and the right, or I shouldn't say left and right, the clockwise and the counterclockwise relation, okay, I mean, let me put them back. P5, okay, obviously, I mean, for P5, okay, if you consider the, final stage, clockwise is P3, counterclockwise is P4, this is the same. But you can see, at the last stage, the clockwise is, for P4 is P5. Counterclockwise for P4 is P2. So it's different, right? It's different. I want to emphasize, okay, the clockwise and the counterclockwise, when you do this removal, may be different from, the final stage, okay? I want you guys to understand that, okay? To note that. To note that. So you remember the clockwise and the counterclockwise neighbor right before you are removed. Right before this side is removed. Okay? Then, okay, so this is, this obviously, takes like a, linear time, right? This takes linear time. And then, okay, so we note, okay, this neighbor information, okay, for PI, when PI was removed, okay, the clockwise neighbor, we note it as CWPI, okay, the counterclockwise neighbor for PI is CCWPI, okay, this is notation. This is notation. Okay, so then, okay, at the beginning, okay, now remember, we are doing incremental algorithm, right? So we will start adding the side one by one, right? Okay, so now, okay, remember we remove all the points up to P4, right? Okay, so only 3 sides are left, right? Only 3 sides are left. And if you only have 3 sides, the construction of the farthest point Voronoi diagram is very easy. Okay, only 3 sides. I forgot. I think there's a this statement. I sort of like a statement. I sort of skipped. Okay, the intersection of the other half planes from the farthest point Voronoi cell for the point is the cell for that point. Okay, what do I mean by other half? Remember, in the Voronoi diagram, I say like a cell can be considered as the intersection of the half planes. Remember, like for every pair of sides, you create a bisector, right? To have like 2 half planes, right? And you keep basically the half that include this side, and then you do the intersection for every such half plane, and you will get the cell for this side, right? So for the farthest point Voronoi diagram, because you want the further away, right? So you are going to keep if this side and the other side you get a bisector, you are going to keep the other half. And every pair you create a bisector, you keep all the other half, and you do like an intersection for all the other half, and the result is the cell. Is the first point Voronoi cell for this side. So if you have 3 sides, you can do this, right? If you have n sides, doing this is, as I said, remember, the intersection, remember I discussed, like, it takes, n squared log n, right? At least n squared log n. Okay, so it's too expensive. But if you have 3 sides, well, it's only constant time, so we can do it like, in constant time, right? Okay, so we have like, we can create like something like a initial, like a first point Voronoi diagram for 3 sides, obviously. And then you add in the 4th side, right? When you add the 4th side, okay, now let's consider if you already have a first point Voronoi diagram for k sides, okay? For k minus 1 side. Now you are adding, well, for I minus 1 side. So now you are adding the pi, okay? You are adding the pi, the 1 additional side. And then, okay, say, this is pi. Where do you consider adding this cell? This cell, okay, will show up between the cells of its clockwise neighbor and the counterclockwise neighbors. Remember, I told you, okay, when you remove each node, remember its clockwise neighbor and the counterclockwise neighbor, right? So and when because you are doing this in reverse order, so when you are adding pi, the clockwise neighbor and the counterclockwise neighbor have already been inserted, right? And you should have a cell for these 2 sides, right? Okay, and let me tell you this, okay? The clockwise and the counterclockwise of pi actually will share one edge. Will share one edge, which obviously is a bisector. It's a bisector of these 2 sides. Okay? So you just find out, for example, if this is pi, this is clockwise pi, this is counterclockwise pi, their cell, okay, you can see, the clockwise pi is here. The cell is here. The counterclockwise pi, the cell is here. And what you do is that you just try to draw like this is the common, edge shared by these 2 cells. And this edge, by the way, happen to be the bisector of clockwise pi and the counterclockwise pi. Okay, and since your cell will appear in the middle, right? You will appear in the middle. So what you can do is that, well, you can do it in either direction, okay? You can do it from, let's say, okay, you do it from the, you start from here, and then you try to go, remember, like, you can, because this is half edges, right? These are the half edges, right? So you just go to here, and then because this edge, as I say, this edge most likely will be completely included in the cell of pi. Okay, so what you do is that you traverse through this edge, and when you traverse to here, okay, this edge you try to see if, for example, you try to draw the clockwise, the counterclockwise pi, and the pi, you draw the bisector. You draw the bisector. You will see this bisector will sort of like intersect one of the boundary of the cell of the counterclockwise pi. Say here. Okay, so this is like after that, this part will belong to counterclockwise pi, but this part inside here, it will belongs to the cell of pi. Okay, so you are drawing this. And then when you hit here, what happens is that, okay, Now, okay, you know this side, this is a side, right? Okay, this is the bisector. When you hit this edge, okay, if you travel to the other, other side of the face, it belongs to the other cell, right? And this cell actually belongs to this cell should belong to somewhat here or here. And then what happens is that, okay, from the face of this, you can find the owner of this cell. And then for these two, for PI and the owner of this cell, you draw again the bisector. The bisector will cut part of this cell. This part of cell will belong to PI now. It kind of like a get a portion of the cell, some part of the cell, to PI. Okay? And then, okay, it will hit this edge, right? Again, it will go to the other side, right? Go to the other side, you try to see, oh, this is this cell belongs to this side. So what happens is that, again, you try to draw the bisector for PI and this side, which is this edge. Okay? And then it will hit another edge here. And then finally, okay, you can see this side, eventually you will find that it belongs to the clockwise of PI. And then, again, obviously, you draw the bisector of PI and the clockwise of PI. And that's it. That's the end. So this is how you add a side. Okay, you will do this for every side you add. Okay, it looks complicated, right? It looks, but actually it's not that hard.
And this ends up n squared in worst case.
We'll discuss that shortly. Okay, any other question? No question? Okay, so you can see once we do this, after that, this part will belong to the cell of PI, and the rest will still belong to the original ones. And then you can try to add another PI plus 1, and so on. Okay. So this is the idea of this algorithm. Okay. And then, okay, this is a detail. So because all the structure is kept in a doubly connected edge list, so you can traverse between half edge, between the corresponding faces. With ease. Okay, not too difficult. Okay, so actually it's even though if you look at this, it looks kind of complicated, but actually it's doable. It's doable. It's not that hard. It's not conceptually, once you understand it. It's just tedious. Okay, as I said, a lot of computational geometry. The work is in the detail. The difficulty part is in the detail, but really, the concept is not that hard. Okay, once you understand it. Okay, so you just add PI one by one. So the cell of PI will come in between the cell of counterclockwise clockwise PI and the counterclockwise PI. So as I already told you. Okay, so then just like a student just asked, how about the complexity? Well, we haven't. Yeah, this is a detail, so I will skip this. The last statement is important. Given a set of endpoints in a plane, its furthest point vulnerable diagram can be computed in big O n log n expected time using big O n storage. Okay, be very careful. Big O n storage is not expected time. Okay, but the computational time is expected time. Okay, Storage, as I say, I mean, you just consider the Voronoi diagram, the vertex in Voronoi diagrams, right? So, I mean, the complexity of the doubly connected edge list is never going to be greater than linear. That's not the issue. But the question is, how do you have the n log n expected time, right? I mean, think about this. During the process, which part takes n log n? The construction of the Voronoi diagram takes n log n, right? Which we have discussed like in the first class of this semester, right? It takes n log n to find out the vertices that belongs to Voronoi diagram. Belongs to convex hull. I'm sorry. The construction of convex hull takes n log n. I'm sorry. Okay? And arrange the vertex in random order. It doesn't take much time, right? Just random swap certain vertexes. That's it, right? And then removal one by one to check the neighbor the neighbor information for each side take linear time, right? So the issue is insertion, right? The issue is in the insertion. How much time does it take to insert each side, right? That's the issue. Okay, so it takes n log n time to compute each point on the convex hull in counterclockwise order, which we know already. So if the cell of Pi has k edges in the boundary, then the traversal performed to trace the cell visit, it will visit k cells in the first point Voronoi diagram. Okay, so this is like in the worst case, you will visit at most 4k minus 6 boundary edges of those cells in total. Why? Because, okay, if you have I sides, okay, okay, remember I told you like exercise 7.14, I mean, has certain instruction to tell you how to prove this. Okay, if you have I sides, you will have at most 2i minus 3 edges. Each, I mean, and up to here. This is remember I told you to prove that number of vertices and number of edges in the first point Voronoi diagram are linear, right? So this is a part of the proof actually. Okay, so remember, okay, when we try to do this digging, okay, obviously you need to, what should I say? You consider the edge. Okay, each edge is considered on two different sides, right? Each edge is considered differently on two. I mean, because of they may belong to two different sides. I mean two. You may consider them twice. Okay, from two different sides. You may go here and then come back, right? But you don't. In the worst case, it's like that. But I mean, you normally only, in this case, in this particular example, you don't see that example. But in the worst case, you may go there and then come back. Okay, you may go in there and coming back. I mean, using the same edge. So going there and coming back, each edge can be used at most twice. Right? Right? So which means what? Which means okay, because we have at most 2i minus 3 edges, right? So the digging, okay, each one can visit at most 2k minus 6 boundaries, right? But this is not each one. Actually, it's for all the sites, for all the k sites. Remember, so here comes the interesting part of randomized algorithm. Okay, in a randomized algorithm, because every sites are considered equally. Okay, So we can sort of consider, okay, these boundaries, these many boundaries, they are, they will be shared by these k sites. And how do they share? They will be shared equally because we are doing this algorithm in randomized order. So we will divide 4k minus 6 by k. Okay, so on average, let me repeat, this is on average. Okay, the expected age you will encounter when you adding, when you add one side, okay, the age boundary you are going to encounter will be less than 4. Because it's going to be 4k minus 6 divided by k. Okay, we can do this computation because the algorithm is randomized. So randomized algorithm, why randomized algorithm is important in computer science? It's because when you do the complexity analysis, it has so many advantages. Okay, which obviously cannot be done like that. In regular algorithm, right? In regular algorithm, obviously you need to consider which one is added first, which one is added second. That's just complicated, just difficult. Okay, so since adding one side is going to involve changing 4 boundaries, only 4, less than 4 on average. So the average time to add one side is constant, right? It's constant. So you are going to add, h sides, right? Where h is smaller than n, right? H is smaller or equal to n, right? So total amount of time is going to be linear. Okay, to construct the furthest point Voronoi diagram. Okay, does that answer your question? Okay, great. Okay, so then, we still have 5 minutes. Good. So, the last slide. So once we are able to create the regular Voronoi diagram, I told you guys, the vertex, the vertex in the regular Voronoi diagram will contribute to the second case. Remember? Okay, so that's great. And the vertex for the furthest Voronoi diagram can be used to find out the first case. Right? Okay. How about the third one? The third one, actually, you are going to overlay 2 Voronoi diagrams together. Okay? And you will be able to find the intersections of some edges. And those intersections could be used, they are candidates for the third case. Okay? And because of that, so given a set P of n points in the plane, the smallest width annulus, and the roundness can be determined in big O n squared time using big O n, linear storage. Okay? You say, wait, how about overlay? Overlay takes n log n amount of time, right? But because overlay, it's going to be lower than n squared anyway, right? And you may ask, how come where does n squared comes from? Because, the intersection could be up to n, right? The intersection of overlay could be up to n, and we need to check everyone. And checking everyone takes linear time. Okay? So it could be, n squared. But that's already worst case. Okay? But still, this is much better than, remember, we do NCN3 to solve the first and second case, not to mention the third one. We don't even know how to solve it efficiently, right? So this one is much better, okay, in terms of the complexity. Any question? You know, this course, like normally, like after about like 1/3 toward like 1/3 of the semester, like I gradually like receiving fewer and fewer questions, and gradually become dead silence. Sometimes I don't even know like if you guys really understand or not. But this class, I mean, we have some students who likes to ask questions, which I think is good. Okay, actually I like to more questions, to be honest. But because at least I know like you guys understand or not. You know, if you don't understand, please let me know. Okay, I'll be more than willing to help. Okay, because this subject, okay, I mean, conceptually it's really not that difficult, but well, maybe I didn't explain clear enough. I mean, maybe your question can help to clarify like some other students' concern as well. Okay, so in any case, I mean, I encourage you guys to ask questions. Okay, have you seen like you guys seen like you know some courses like taught in online? There are some like courses that gets recorded like in US. Okay, for example, like some Harvard course, they just record like the like this. Okay, they just record the course like you know so you can see like students just like asking questions like crazy. You know when professor asks like any question, a lot of students like more than half of the students raise hand actually. But in Taiwan, I know this is like too much to ask. Yeah, but anyway, I mean, well, we are running out of time. So any question? Okay, so that's the end for this. Don't, as I said, don't worry about the assignment at the end of the slide. Okay, I mean, do the homework which are posted on the EE class only. Okay, so don't worry about that last slide. Okay, so no question. So let's call it a day. Okay. Thank you. So I will not see you next week because next week is a holiday. So I'll see you the week after next, which, by the way, is midterm. Don't forget that, please. And if you have checked out the sample midterm, you will see that the sample midterm are actually easier than the homework, right? I mean, if you really check it out, I mean, you know I'm true. You know I'm right. Okay. So if you know well for all the questions that I ask in the homework, I mean, it shouldn't be difficult for you. Okay. Okay. So see you in 2 weeks then. Okay. Bye.